So far, we have had discussions on MOS transistor basics, operation, large signal behavior, small signal behavior, their second order effects, their scaling, their leakage current mechanism, and all these things. And now we'll move on to a new topic called the inverter. Okay, so this is CMOS inverter. CMOS inverter basics. Okay, let's start with CMOS inverter basics. So first, let me give an introduction. Okay, so as to how this inverter is established, or the circuitry of the inverter as such. Okay, first of all, let's start with what we know earlier. We had actually we had done something like a MOS transistor. Okay, this much is what we know. Okay, so this is some kind of an voltage, and this is the source, and this is the input voltage or the gate and this is the drain. Okay, so you have a situation like this. Okay, so what happens, so if suppose you want some kind of you want this to operate as an inverter, say. Okay, so meaning I know what is an inverter. If I give 1, I should get 0. If I give 0, I should get 1. Okay, this is what I want. So meaning I will now think in terms of voltage levels. If I give some voltage, high voltage, then I should get low voltage at the output. Okay, and if I give low voltage, I should get high voltage at the output. So obviously my choice would be to have some kind of a resistor here, load resistor, and take an output here. Okay, and if this is high voltage VDD, so what happens, if I give some kind of an input voltage, okay, which is higher than VTH, then this transistor will conduct and the path will be shorted and all the output will be going to 0. Okay, and if I give an voltage that is less than VTH, this path will be open and all the voltage will be going to the voltage will be going to Vout will be going to VDD, because there will be no current flow as such. Okay, when this transistor is off, it will go to VDD itself. But then how do we estimate it? Okay, how do we estimate all these things? You can do it graphically. Okay, how do we do it? You actually draw the current of the MOSFET for different input voltage. You draw the current through the resistor, and then this will be a load line now, and then you see the points of intersection and try to estimate Vout from there. It's as simple as that. So let me draw the output characteristics. VDS, in this case VDS is nothing but Vout, right? Vout, D and S is grounded, so VDS is Vout. And let me draw the ID of the MOSFET, and I know that there will be some kind of a parabola line, VGS minus VT, and VGS is Vn. Okay, and then beyond which the current will saturate, and it goes on parabolically increasing current, and then it goes on like that. Okay, now this is Vn1, Vn2, Vn3, and so on and so forth. Okay, so now what will be the voltage, what will be the load line of current through this particular resistor that will act as a load line, which is nothing but I resistor is IRL is equal to VDD minus Vout by RL, right? So how do I draw the load line? So the load line can be drawn easily. This is an equation, you have to put it here. You just have to find the two intercepts. When Vout is equal to 0, you are going to get the intercept somewhere here, which will be VDD by RL. And when IRL is equal to 0, this point, you are going to get this intercept, which is nothing but the VDD itself. Okay, and then connect these 2 points. So this is the load line, right? Now each current due to the currents due to each input, wherever it's intersecting the load line, okay, these points are my Vout points. Okay, so let me put it as a graph. Vout versus Vin. Okay, if I have Vout versus Vin, then what happens? First of all, when Vout is equal to 0, that means when VD is equal to 0, current is 0. Okay, so, or no, I'm sorry, this is wrong. This is V in and this is V out. Okay, V in versus V out is what we have to draw. Basically the slope of this is the gain, right? So output versus input. So when V in is equal to 0, what happens? When V in is 0, current is 0, right? And when current is 0, current 0 is this line, okay? And it intersects the load line at VDD. So I am going to get an output voltage of VDD when V in is 0. And how long will my current be 0 for, what value of V in? Up to threshold voltage, okay? Up to threshold voltage, the current is going to remain at 0 volt, okay? Current is going to remain at 0 amps, and then the intersection will be at VDD. So I will get some situation like this, okay? Beyond which my current starts reducing, okay? Beyond which my current starts increasing and my V out starts reducing, okay? Because the intersection point shifts like this. So at somewhere around this V in, my point will be somewhere here, and this V in, my point will be somewhere here, and so on like that. And as I go closer and closer, my V in goes closer and higher and higher to VDD. Say for example, my V in is increasing somewhere here like this, and somewhere it increasing like this, and so on like that. Then you see that it will never go to this point where my VDS or V out is equal to 0. It will never reach a point where V out is equal to 0. Okay, so V out is 0 is this point. It will never intersect at this point. Okay, that is what I am trying to say. So you will always have some kind of a leakage. Okay, you will have something like this even at VDD. V in is equal to VDD. Okay, this is the scenario. This is what you get. Okay, and does it act as an inverter? Logically yes, because you give some kind of a low input, it gives high value at the output. You give some kind of high input, it gives some low value of the output. So it acts as an inverter. True. But what is the problem with such an inverter? The problem is that it has something called a noise margin that we will declare later. Like sufficient amount of margin should be there. Okay, so what I mean by that is, I want an ideal inverter to behave something like this. I give some kind of V in which is lower than some marginal value. It will always give VDD, and beyond that it will always give 0. Okay, but it is not so. And second thing is, when this transistor is on, there is some kind of, actually this transistor is on, but to draw the output to 0, but then there is some kind of current flow from VDD to source or to the ground, right? Which basically means some leakage current is there existing. Okay, so it's a dynamic leakage. When the transistor is operating, there is some leakage current which I don't want. So you have issues with noise margin, you have issues with power dissipation. So we have to sort out this, and the main reason is that this slope. Okay, the slope is turning out to be the main reason, and the slope is nothing but the gain, and it basically means that the gain is smaller because it's a passive load, right? And the gain of from the small signal model, when a load is connected, you can say the gain is equal to minus GM times RL, and this load is passive. Okay, so obviously you cannot get a higher gain if the RL is fixed. If you have a higher gain, the slope will be very large, right? If the slope is very large, then you will have sufficient noise margin and all these things will happen. Okay, so how to get a higher gain is the question. So you will get higher gain when RL tends to infinity, because gain is minus GM RL. If RL tends to infinity, gain will be larger. But can I do that? Can I have a very large gain, a very large RL? It turns out that I cannot have a very large RL, because if I have very large RL, this voltage drop VRL will also increase. Okay, if I have a large drop here, what happens is that my VDD is fixed. Okay, so I will drop all the VDD at the resistor only, and nothing will come out at the voltage. Okay, output voltage. So if nothing comes out to be at the output voltage, then this transistor will not remain in saturation. Okay, and only when it remains in saturation you will get a very large slopes like this. Okay, that is when the gain will be maximum. So I am actually greedy to want a larger resistance, okay, at the load, but I cannot have it because if I have it, then I will have a large voltage drop that will actually make my transistor come out of saturation and I will not have this slope. Okay, so how to solve this issue? So you can actually graphically try to understand what we just said. We said that when you plot this drain voltage output versus some current, okay, so MOSFET is providing some constant current in saturation region with respect to the drain voltage. Okay, output voltage is the drain voltage. So with respect to the saturation region, MOSFET is providing some constant current, let's call it ID. Okay, and current, there is some current through the resistor. Okay, and the current through the resistor, if you draw the current versus voltage plot, then you will have something like a linear line, right, something like this, and slope of which is 1 by R. Okay, and wherever they intersect, this is the output voltage, or this is the drop across the resistor, right, you can say like that, this is the drop across the resistor. So but what I want this resistance to be very large. Okay, I want the resistance to be very large, meaning the slope should be very, very small, because resistance increases, slope reduces. I want the slope to be very small like this. If the slope is very small like this, it will intersect this line somewhere here, meaning the drop across this particular resistor will be very large. That is what it means, this voltage will be very large. Okay, so this is something I don't want. I don't want this I'm sorry, this is not V out, this is some V, this is not output voltage, this is some V, this is VRL, this is V, this VRL will be very large, here the VRL is very small. Okay, voltage drop across the resistor. So now I don't want this voltage to be very large, right, but I want to have a very large resistance. So indirectly what I am saying, I want this line to come here, meaning I want the slope of this line but to intersect this line, this point. Okay, to pass through this point, I want a line that passes through this point but has the slope of this line, right. So if I can actually specify 2 points to draw a line, or a slope and a point, right. So now I have specified this is the slope of that, this is the slope of that line that I want, and this is the one point where I want it. So nothing else, I cannot specify anything more. So I will have a situation like this, right, and this will obviously touch here if it extended, because the line that we are drawing, it's now non-linear, right, because linear will pass to the origin, it's going to be non-linear. And so let me use some other color for illustration. Okay, so this is what I want, this blue line is what I want. Okay, this black is what I have. So this is what I want. So if it is passive, if the device that I'm talking about, which will give this line, is passive, okay, then it has to pass through the origin. The curve has to pass through origin, meaning its characteristics will lie either in first quadrant or third quadrant, meaning the I into V should be positive for a passive device, right, and all devices that will take are passive. So it will look something like this, right. So if you see this particular line, it looks like a MOS transistor characteristics. It's a MOS transistor characteristics. Previously what we had, this line and this line are all linear resistor characteristics. Now it appears that this particular line is like a MOS transistor characteristics, which we often draw something like this, and smaller the slope, better it is for me to have even more higher gain, right. And if you have channel in modulation, you will have some finite slope, that also we saw, VDS versus ID, right. So I should replace this resistor. If I replace this resistor with a MOS transistor, then I will actually have whatever I desired or whatever I intended to have, right. So now let us see which MOS transistor to put, because we know that we have an NMOS and a PMOS. So here in this course, let me actually differentiate the NMOS and PMOS with a bubble. PMOS will have a bubble. Okay, and this is source and drain, and this is source and drain and gate. Okay, this is also gate. Now I could either use NMOS or PMOS because both will have same characteristics, right? It's just that the voltages will be VGS and VSG and VDS and VSG here and there. So we have discussed that already. Now let us see which one to use. Actually, if you use, we are talking about using a MOS transistor instead of a resistor. In the place of a resistor, I will use a MOS transistor to yield my output. And let's see, it's a capacitor I am drawing as a load capacitor, so that I will see how it charges and discharges. So if I use an NMOS transistor, okay, if I use an NMOS transistor gate, now it's interchangeable, right? It could be source, it could be drain, or it could be drain, it could be it could be source, it could be drain, it could be anything. Okay, so if you connect an NMOS transistor, how would you connect it? First of all, if it is a source, if this is source and this is drain, and say you give VDD to the gate, okay, what happens? VDD is the maximum voltage that you can give. If you give like that, this is also VDD, this is also VDD. So VGS is equal to 0, and you need at least VT for it to conduct, for a MOS transistor to conduct. Now VGS is 0, it will not at all conduct. So you cannot give source and drain like this. Okay, so you interchange now. If it is drain and this is source, what happens? So again you give a VDD here, okay, and now this is drain and this is source. And of course, assume that source voltage is initially at 0. This capacitor is completely discharged, initially at 0. So now it will start, the voltage from the drain will start appearing at the source. Okay, so because it's like it will pass, whatever is there at the drain will be passed here, because current will be from drain to source. Whatever is there at the drain will be passed to the source now. Okay, and it will start charging. So the voltage at the capacitor will start increasing from 0 to VDD. Okay, but will it actually reach VDD is the question, because say it is increasing, it keeps on increasing, and it reaches some VDD minus X. Okay, it keeps on increasing, meaning the voltage across the capacitor will keep on increasing. It will go on having some value, and then say it is reaching some kind of a value where it is VDD minus some X value. If this X becomes close to threshold voltage, okay, what happens? So through source voltage is VDD minus VTH, or threshold voltage VT. Now gate source becomes VGS is equal to VDD minus VDD, because this is source voltage now, plus VT, right? So it becomes VT. So now VGS is equal to VT. Okay, so beyond which, if this voltage will not increase, because if it increases, this MOS transistor will not conduct. Okay, so the moment it reaches beyond that, VGS will be less than VT, and this MOS transistor will not conduct, and it will stop like that. So the maximum voltage that you can receive is only VDD minus VT at the output, which is something that I don't want. Okay, so what to do? Obviously try another MOSFET, because both combinations not possible. Source and drain connected this way is not at all working, and drain and source connected this way is giving me some output, but it cannot give me more than VDD minus VT. Okay, so take the next MOSFET, P MOSFET. Okay, so now you connect, this is VDD, and you take the next MOSFET, the gate, V out, you put a capacitor. Now which way you can do? Okay, it could be source or this could be source. Okay, so let me put it first, this is drain and this is source. If I put like that, what happens? Okay, so here the condition for PMOS to conduct is VSG should be greater than the modulus of threshold voltage of PMOS. Okay, so what happens to the if I put in this manner, if this is drain and if this is drain and this is source, the drain voltage, which is now VSD, okay, so let me assume initially the source is at 0, okay. For PMOS to conduct, I have to give 0 at the gate, okay, then only VSD will, you know, if this is maximum, it will conduct or whatever, right? So right, for PMOS I should give 0 at the gate, and I am assuming source is at 0 also. Now VSG, is it greater than VTP, modulus VTP? No, not at all, because VSG is 0, it will not work at all. So I cannot give this combination. So I should give this as source and this as drain. If I do so, then VSG is equal to VDD, okay, and VSD is equal to VDD also, okay. So it will conduct, VSD also is equal to VDD, it will conduct smoothly and it will transfer the 1 here, and there is no issue like VDD minus VT or something, because PMOS is a very good conductor of passing 1, okay. So gate voltage, as long as it is 0, the source will pass the VDD here, and VSD will always be remaining at VSG will always be remaining at VDD, which is much higher than VTP, okay. So this will always conduct, and all the VDD will appear here at the output, so 0 will turn to VDD, okay. So this is something that is desirable for me, and as you would have figured out by now, just like PMOS, which is a good good conductor to pass logic 1, NMOS is a good conductor to pass logic 0, and of course it's a bad conductor to pass logic 1, and PMOS is a bad conductor to pass logic 0, okay. So given this idea, so how we will construct the inverter? We will construct the inverter simply like this. You will replace the resistor which was earlier by a PMOS, and already there was an NMOS, and you connect both the inputs, okay, and then you give it as an input, and then you give VDD here, and then you take the ground here, and you take the output here, okay, and some kind of a capacitor is there, okay, which will show you the charging and discharging of the output. So this is essentially the CMOS inverter, okay. So we'll see in the next sessions, we'll see what are the voltage transfer characteristics, noise margin, power dissipation, and the behavior of an inverter, and all these things, okay.